In this video, we'll uncover the secrets behind the F-117 Nighthawk's groundbreaking stealth capabilities. You'll learn how its unique design allowed it to scatter radar waves, making it almost undetectable. We'll explore the incredible ingenuity behind its radar-absorbing materials, the engineering marvel of its flight systems, and the intense development process that remained shrouded in secrecy for years. Join us as we delve into the story of the Nighthawk, from its first classified test flights to its pivotal role in modern warfare, transforming not only aviation but also the future of military strategy. Don't miss this deep dive into one of the most extraordinary aircraft ever built. Origins of stealth technology. The quest for aircraft invisibility began long before the F-117 Nighthawk airplane took flight. During World War I, German engineers experimented with Selen, a transparent covering material, in an attempt to make military aircraft invisible to the naked eye. This early attempt proved ineffective and even counterproductive, as sunlight reflecting off the material made aircraft more visible. The concept of radar-evading aircraft gained momentum during World War II. The German Horten Ho 229 flying wing fighter bomber represented an early attempt at radar evasion, though claims about its stealth capabilities were later disproven through testing conducted by Northrop Grumman in 2008. The true breakthrough in stealth technology came from an unexpected source. In 1962, Soviet mathematician Pyotr Ufimtsev published a groundbreaking paper titled Podded Edge Waves in the Physical Theory of Diffraction. While the Soviet Union showed little interest in his work, this publication would later become the foundation of modern stealth aircraft design. Ufimtsev's research focused on calculating how electromagnetic waves reflect from surfaces, particularly edges and vertices. In 1975, Lockheed's Skunk Works division embarked on a groundbreaking journey to transform the theoretical insights of Soviet physicist Pyotr Ufimtsev into practical stealth technology. Engineer Denis Overholser played a pivotal role in this endeavor when he discovered a translated version of Ufimtsev's paper, which detailed how the shape of an object could be manipulated to reduce its radar visibility. Building on this foundation, Overholser developed a revolutionary computer program named Echo-1. This program enabled precise predictions of radar signatures for aircraft designed with flat, angular panels, laying the groundwork for a new era in aviation design. The culmination of this research was the creation of the HAV Blue prototype, a testbed for what would become the F-117 Nighthawk. The results were nothing short of astonishing. The prototype achieved a radar cross-section so minuscule that it was comparable to the size of a ball bearing, rendering it thousands of times less detectable than the stealthiest aircraft of its time. Against most ground-based missile tracking systems, it was virtually invisible, effectively rewriting the rules of aerial combat. Only the highly specialized Boeing E-3 awakes, equipped with advanced radar systems, could detect the aircraft, and even then, only at very short ranges. The HAV Blue program, costing $37 million for 2 prototypes, validated the concept of faceted surface geometry for radar deflection. Despite both prototypes being lost during testing, one in May 1978 and another in July 1979, the program's success led directly to the development of the F-117 Nighthawk airplane. The Defense Advanced Research Projects Agency awarded Lockheed the contract for the Nighthawk less than a year after HAV Blue's successful first flight in 1977. Revolutionary design principles. Breaking with conventional aircraft design principles, Lockheed's engineers created a revolutionary approach to achieve radar invisibility. When initially presented with the stealth concept, Skunk Works director Kelly Johnson advocated for smooth, rounded surfaces. However, his assistant Ben Rich demonstrated that angular, flat surfaces would provide superior radar signature reduction. The F-117 Nighthawk's distinctive appearance emerged from a technique called faceting, breaking the airframe into a series of flat, angular surfaces. These trapezoidal and triangular panels were precisely arranged to scatter incoming radar waves away from their source. The design was so unconventional that when a Royal Air Force pilot first saw a photograph of the secret aircraft, he reportedly laughed in disbelief at its apparent inability to fly. Key design features included V-type windshields similar to the F-102 F-106, and circular paper with carefully sealed panel joints and access doors, and serrated panel boundaries to deflect radar energy. The F-117's radar cross-section achieved an unprecedented 0.001 square meters, making it comparable to the size of a marble. This remarkable reduction resulted from combining the faceted geometry with radar-absorbing materials RAM. The RAM application required meticulous attention to detail. Even a single loose screw could make the aircraft appear like a barn door coming over the horizon during radar signature tests. The F-117's angular design was largely influenced by the technological limitations of the 1970s. Early computer modeling could only calculate radar reflections from flat surfaces, making curved surface analysis computationally impossible. Using a Cray supercomputer, engineers developed the Echo-1 program to predict radar signatures from faceted shapes. The effectiveness of this approach was dramatically demonstrated during initial testing. When a wooden model dubbed the Hopeless Diamond was placed on a radar test range, operators could not detect it until a bird landed on top of the model. They were only picking up the bird's signature. This success validated the computational approach and secured Lockheed's position as the project leader, particularly because they possessed the only computer model capable of predicting radar signatures. The aircraft's design proved inherently unstable around all three axes, requiring sophisticated flight control computers for stability. This challenge represented one of the first applications of comprehensive fly-by-wire technology, marking another significant advancement in aviation engineering. Materials engineering innovation. Materials engineering played a crucial role in making the F-117 Nighthawk plane virtually invisible to radar. The aircraft's stealth capabilities relied heavily on innovative materials that pushed the boundaries of aerospace technology. The F-117's radar-absorbing material represented a significant engineering achievement, weighing approximately 1 ton. Early versions utilized metal-backed ram tiles containing carbonyl iron ferrite, which created alternating polarity magnetic fields when encountering radar waves. This innovative material converted incoming radar energy into heat, effectively reducing the aircraft's detectability. The ram coating achieved remarkable performance metrics. It absorbed more than 90% of incoming radar waves, drastically minimizing the aircraft's reflectivity. This capability contributed to an almost negligible radar cross-section of just 0.001 square meters, making the F-117 appear no larger than a small bird or an insect on radar screens. Additionally, the material was engineered to function effectively across a broad spectrum of radar frequencies, ensuring its stealth capabilities remained robust even against diverse and sophisticated detection systems. This engineering marvel not only underscored the technological prowess behind the F-117, but also cemented its legacy as a transformative achievement in modern aviation. The application of RAM required precise engineering and meticulous attention to detail. Maintenance crews filled gaps between RAM sheets with a specialized putty material nicknamed butter. This careful sealing process ensured no radar-reflecting surfaces remained exposed. Later versions of the F-117 Nighthawk utilized direct application RAM paint, though this coating was known to be highly toxic. The surface coating system incorporated multiple protective elements. Engineers installed conductive metal mesh grills in the intake areas to prevent radar waves from reflecting off engine components. The exhaust system featured a specialized design that mixed cool air with exhaust gases to reduce the aircraft's thermal signature. Despite the complex material requirements, engineers developed innovative solutions to maintain structural integrity while preserving stealth capabilities. All doors and opening panels featured saw-toothed edges to deflect radar signals. The aircraft's maintenance design showed particular ingenuity, with access panels strategically placed within landing gear and weapons bays to minimize the need for frequent RAM removal. The engineering team made significant efforts to simplify maintenance procedures while maintaining stealth effectiveness. They designed hexagonal panels for the aircraft's underside, aligning all lines parallel to the wing's trailing edge. This careful attention to detail ensured that any radar returns from access doors would be masked by the wing's minimal signature. The material system proved remarkably effective, though it faced certain limitations. The ram coating could not withstand temperatures above 250 degrees Celsius and remained vulnerable to environmental factors such as heat, salt, moisture, and friction. These constraints required careful consideration during mission planning and regular maintenance schedules to maintain the aircraft's stealth capabilities. Propulsion system design. The propulsion system of the F-117 Nighthawk airplane represented a masterful balance between stealth requirements and operational capability. At its heart, the aircraft utilized two modified General Electric 404 turbofan engines, each producing 13,000 pounds of thrust. The F-117's engine inlets featured innovative design elements crucial for maintaining stealth characteristics. Engineers installed specialized gratings with rectangular openings over each intake, preventing radar waves from reaching the engine's rotating components. These gratings were smaller than typical radar wavelengths, effectively blocking electromagnetic energy while still allowing sufficient airflow. To compensate for restricted airflow during critical flight phases, the design incorporated large blow-in doors atop each engine nacelle. Key engine inlet features included offset inlet designed to shield engine components, ram-coated intake gratings, an electrical heating system for ice removal, and secondary air intakes for optimal performance. The exhaust system presented one of the most challenging aspects of the F-117's design. Engineers developed a sophisticated solution that transformed the conventional round engine exhaust into a 17-to-1 flattened, slot-convergent nozzle. This unique configuration included: the exhaust system integrated an array of advanced features to achieve its objectives. 12 grated openings, each roughly 6 inches square, facilitated the even dispersion of exhaust gases while minimizing the heat footprint. To further manage heat and protect the aircraft's structural components, heat-reflecting ceramic tiles were installed along the rear edge of the exhaust assembly. These tiles served as a thermal shield, reflecting intense heat away from critical areas. In addition, a bypass air cooling system was incorporated to regulate exhaust temperatures, ensuring they remained below detectable thresholds. The system also included complex sliding elements that allowed for heat expansion, preventing structural stress and ensuring the durability of the exhaust system during high-temperature operations. These innovative features represented a masterpiece of engineering, solving a critical technical hurdle and solidifying the F-117's reputation as a marvel of stealth technology. Despite the constraints imposed by stealth requirements, engineers achieved remarkable performance optimization. The F-117's engines underwent extensive modifications to produce minimal mass thrust, facilitating easier inlet and nozzle design integration. The aircraft could maintain speeds exceeding 1,100 km/h and demonstrated exceptional range capabilities, setting a record for the longest single-seat fighter mission at 18.5 hours. The propulsion system's design addressed multiple technical challenges. The exhaust gases were intentionally mixed with cool ambient air to reduce the thermal signature, while the non-circular tailpipe minimized the exhaust cross-section. This careful balance of performance and stealth characteristics enabled the F-117 to maintain its radar cross-section of approximately 0.001 square meters. A specialized company, Aztec MCI, designed the distinctive exhaust system in just 10 months, creating a nickel alloy tailpipe with a unique honeycomb design. This innovation effectively flattened the exhaust while concealing the rotating turbine blades of the twin engines. The system proved so complex that Lockheed reported it as the single most challenging component of the entire F-117 project. Avionics and control systems. Advanced control systems formed the backbone of the F-117's remarkable capabilities, enabling precise flight control despite its inherently unstable design. The sophisticated integration of computers, navigation systems, and pilot interfaces made this unconventional aircraft operational. The F-117's aerodynamic instability around all three axes demanded constant computer intervention. Engineers implemented a quadruple redundant fly-by-wire system adapted from the F-16, though extensively modified to handle the unique flight characteristics. This system translated pilot inputs into electronic signals, processed by multiple onboard computers for precise flight corrections. The aircraft's brain consisted of 3 IBM mission computers derived from space shuttle technology. These computers integrated with the IBM F-102 mission control computer, which managed a fully automated flight management system. Before each mission, detailed flight data would be uploaded to these computers, coordinating navigation, flight stability, and weapons targeting with unprecedented precision. The navigation suite of the F-117 Nighthawk marked a groundbreaking step forward in aerial guidance technology, incorporating a range of sophisticated systems to ensure precise and reliable performance during missions. At the heart of the system was the Honeywell Ring Laser Gyro Inertial Navigation System, a state-of-the-art solution that provided accurate and drift-free navigation without relying on external signals. This was seamlessly integrated with GPS technology, which used low observable antennas to maintain the aircraft's stealth profile while enhancing positional accuracy. Additionally, an automated mission planning system was implemented, enabling pilots to pre-program complex flight paths, while 4-dimensional flight management capabilities ensured adherence to precise time on target and spatial requirements. The navigation system underwent significant improvements through the Ring Laser Gyro Navigational Improvement Program. The upgraded system replaced the original B-52 Honeywell Speen Jeans INS, which required over 40 minutes to align with the more efficient Honeywell H-123 Laser INS. This enhancement, combined with GPS integration, dramatically improved navigational accuracy and reduced alignment time. The cockpit layout evolved to optimize pilot effectiveness while minimizing workload. The cockpit featured a Kaiser Electronics head-up display, which projected critical flight data directly into the pilot's line of sight, allowing for heads-up situational awareness. Twin-color multifunction display indicators provided versatile and detailed mission information, while a Harris Corporation digital moving map system offered real-time geographical awareness. Complementing these were a liquid crystal data entry panel capable of managing 256 avionics functions and a large central video monitor that displayed infrared imagery, essential for target identification and navigation during night operations. The pilot interface underwent significant modernization under the Operational Capability Improvement Program Phase II. This upgrade replaced the original central fleur-de-lis display with a digital moving map display, while infrared imagery moved to one of 2 Honeywell color, multifunction LCD screens. These improvements specifically addressed pilot disorientation during nighttime operations, which had contributed to several operational incidents. The integration of these advanced systems allowed pilots to focus on mission execution rather than basic aircraft control. The automated planning system could perform all aspects of an attack mission, including weapons release, while maintaining the aircraft's stealth characteristics. This sophisticated combination of flight control, navigation, and interface systems transformed an aerodynamically challenging design into a highly effective strike platform. Manufacturing challenges. Building the world's first stealth fighter demanded unprecedented precision in manufacturing processes. The F-117 Nighthawk airplane's production journey represented a unique blend of innovative assembly techniques and rigorous quality control measures. The manufacturing process began in Building 82, the birthplace of several legendary aircraft, including the U-2 and A-12. Engineers utilized just 4 primary assembly tools for the entire aircraft, covering wing, forward fuselage, aft fuselage, and boom sections. The assembly process required extraordinary attention to detail, as even minor imperfections could compromise the aircraft's stealth capabilities. Key assembly components included precisely aligned panel joints, specialized radar-absorbing material application, custom-designed assembly fixtures, and surface coating verification systems. The manufacturing process incorporated stringent security measures and quality checks. Each worker required secret-level security clearance, with initial core staff numbering approximately 75 before expanding to several thousand. The program director personally interviewed every team member to ensure security compliance. Quality control was executed with meticulous precision, employing a systematic, multi-phase approach that spanned the entire manufacturing process. The first step involved pre-assembly verification of all components to ensure they met design specifications and were free of defects. Following this, surfaces were subjected to detailed validation checks to confirm they adhered to the precise specifications required for radar-evading performance. Specialized testing was then conducted to measure the radar cross-section of individual components and assemblies, ensuring that every part contributed to the aircraft's stealth capabilities. Once these preliminary stages were completed, the final assembly underwent comprehensive inspections to verify structural integrity and alignment. The last phase involved operational systems testing, during which all avionics, propulsion systems, and other critical subsystems were rigorously evaluated to ensure they functioned flawlessly under operational conditions. The program maintained exceptional quality standards while operating under strict security protocols. Workers awaiting clearance were assigned to the Icebox, a specialized shop where they worked on non-classified components. The F-117 program pioneered several manufacturing innovations that balanced efficiency with stealth requirements. Engineers made a strategic decision to utilize existing components from other aircraft, allowing them to focus resources on stealth technology development. One key aspect of this strategy was the integration of engine components from the F-18's GE-404 system, which provided reliable and efficient propulsion. Similarly, the cockpit layout incorporated equipment derived from the designs of the F-16 and F-18, ensuring familiarity for pilots transitioning to the new platform while maintaining high functionality. Navigation systems, originally developed for the B-52 bomber, were modified to suit the F-117's stealth profile, enhancing its precision while keeping costs manageable. Environmental controls, essential for maintaining pilot comfort and operational readiness, were adapted from the C-130 transport aircraft, demonstrating the program's resourceful approach to non-stealth specific components. Additionally, flight control computers based on F-16 systems were carefully modified to manage the Nighthawk's unconventional aerodynamics, ensuring stability and maneuverability despite its angular design. The manufacturing process evolved significantly with the introduction of the single configuration fleet program. This initiative consolidated 7 different radar-absorbing material configurations into a single optimized design. The new approach reduced maintenance requirements by over 50% while improving overall effectiveness. Production efficiency benefited from streamlined management by the Aeronautical Systems Center at Wright-Patterson AF. This approach combined breakthrough stealth technology with concurrent development and production cycles. The program achieved initial operational capability in just under 5 years, approximately half the typical timeframe for comparable aircraft programs. Manufacturing innovations extended to the coating process, where robotic systems eventually replaced manual application methods. The first Nighthawk refurbishment required 4.5 days with 5 painters and a masking crew. Later, the introduction of advanced robotic painting systems, featuring 3 commercial Mottoman Pete robotic arms, significantly improved efficiency and coating consistency. The program demonstrated that stealth aircraft could be manufactured with reliability and maintainability comparable to conventional tactical fighters. This achievement came despite the additional complexity of working with radar-absorbing materials and maintaining precise surface specifications throughout the manufacturing process. Testing and validation. Validating the world's first operational stealth aircraft required pioneering new testing methodologies and verification processes. The Defense Advanced Research Projects Agency initiated comprehensive testing protocols to ensure the aircraft's revolutionary capabilities met stringent military requirements. Initial radar cross-section testing utilized an innovative approach with pole-mounted models. During early development, Lockheed placed a large-scale model on a radar test range in Nevada to evaluate its stealth characteristics. The results exceeded expectations. Radar technicians initially believed the model had fallen off the pole when they received no return signal. The only radar signature detected came from a bird that had landed on the model during testing. The testing program revealed several groundbreaking achievements. The model achieved an unprecedented radar cross-section of just 0.001 square meters, making it virtually invisible to radar systems. This reduction in radar detectability rendered the aircraft undetectable by the majority of ground-based missile tracking radars, a critical capability for stealth missions. The testing also demonstrated the model's effectiveness across a wide range of radar frequencies, showcasing its versatility and robustness in countering diverse detection systems. Furthermore, the design required only minor adjustments to maintain its stealth properties, highlighting the precision and ingenuity of the initial engineering efforts. These early successes in radar cross-section testing not only validated the theoretical foundations of stealth technology, but also provided the confidence needed to advance the F-117 program. They underscored the revolutionary nature of the aircraft's design and solidified its potential to redefine the standards of modern aerial combat. The flight testing phase proceeded through carefully planned stages. The first F-117 completed its maiden flight from Area 51 on June 18, 1981, marking the beginning of an intensive evaluation period. 5 full-scale development aircraft, designated F-117A, underwent comprehensive testing to validate the design's capabilities. The program faced several significant challenges, such as a shortage of aerospace workers with required security clearances, complex avionics integration issues requiring specialized testing, an extended weapons certification timeline due to instrumentation requirements, and a need for consistent test parameters across multiple aircraft configurations. To address these challenges, Lockheed formed a specialized Tiger team led by their chief scientist. This team streamlined the testing process by designating a single aircraft and pilot for specific test sequences, ensuring consistent evaluations. Performance verification extended beyond basic flight characteristics to encompass the entire weapons system. The program required 48 individual test plans, with essential testing completed before achieving initial operational capability in October 1983. Engineers continued supplementary testing for several years afterward to fully validate all operational parameters. The verification process included innovative solutions for testing stealth characteristics. Ground crews developed precise protocols for maintaining the aircraft's radar-absorbing materials between test flights. This included careful inspection of all panel joints, proper torquing of surface screws, and application of conductive tape where needed. The F-117 Nighthawk airplane's testing program validated its unprecedented capabilities while establishing new standards for stealth aircraft verification. Test pilots completed more than 65 specialized test sorties to evaluate the aircraft's response to various radar threats. The successful completion of this comprehensive testing program confirmed the F-117's ability to operate effectively in heavily defended airspace while maintaining its extraordinary stealth characteristics. Technical limitations. Despite its groundbreaking stealth capabilities, the F-117 Nighthawk plane faced significant technical constraints that shaped its operational profile. These limitations stemmed from the necessary trade-offs between stealth requirements and conventional aircraft performance. The F-117 Nighthawk's distinctive angular design created inherent flight challenges. The aircraft exhibited instability around all 3 axes, pitch, roll, and yaw, requiring constant computer intervention for stable flight. This instability necessitated a sophisticated fly-by-wire system derived from the F-16, though extensively modified to handle the unique flight characteristics. The aerodynamic design imposed several critical limitations, including subsonic speed restriction to prevent airframe heating, high sweep angle, 50 deg, for radar deflection, very low wing aspect ratio, affecting maneuverability, and no afterburner capability to maintain stealth. These design choices resulted in an aircraft that sacrificed dogfighting capability for stealth effectiveness. The pressure distribution around the aircraft revealed highly undesirable aerodynamic properties, including an unusually large high-pressure area in front of the cockpit and engine intakes. Maintaining the F-117 Nighthawk's radar-absorbing materials RAM was an intricate and demanding process, requiring meticulous attention to detail to preserve the aircraft's stealth capabilities. The initial design featured 7 distinct RAM configurations, each tailored for specific areas of the aircraft. While these configurations enhanced stealth performance, they also introduced substantial logistical challenges for maintenance teams. Every step of the process demanded precision to ensure the integrity of the radar evading surfaces. Maintenance procedures included the regular inspection of surface coatings to detect and address any wear or damage. Panel joints had to be carefully sealed to prevent radar wave leakage, and every surface screw needed to be tightened to exact torque specifications to avoid creating reflective gaps. When applying the RAM paint, the process required maintaining precise distances during spraying to ensure uniform thickness. Specialized masking procedures were also employed to protect sensitive areas during recoating, further emphasizing the level of detail involved in maintaining the aircraft's exterior. Early refurbishment efforts were particularly labor-intensive. The first Nighthawk overhaul required a team of 5 painters and a dedicated masking crew, working for 4.5 days to complete the process. Even minor deviations, such as an air bubble beneath the coating or an improperly tightened screw, had the potential to compromise the aircraft's stealth properties. These exacting standards reflected the critical role of RAM in the F-117's operational success, highlighting the extraordinary commitment required to maintain its cutting-edge capabilities. The F-117 Nighthawk bomber operated under strict limitations to maintain its stealth effectiveness. Without radar equipment, the aircraft relied solely on passive navigation and targeting systems. This absence of active radar, combined with other design compromises, resulted in several operational constraints. The aircraft faced significant challenges. One of the primary challenges was the aircraft's limited weapons capacity. The F-117 could carry only 4 1,000-pound bombs, which, though sufficient for precision strikes, restricted its ability to engage multiple or heavily fortified targets in a single mission. Additionally, the Nighthawk was equipped with no defensive armament, leaving it entirely reliant on its stealth capabilities to evade enemy detection and engagement. In combat scenarios, the aircraft's maneuverability was notably restricted, and a compromise was made to optimize its radar deflecting geometry and stealth profile. This limited its ability to perform high-speed evasive maneuvers or adapt to dynamic threats during operations. Further complicating its deployment were its unique maintenance requirements. The F-117 demanded highly specialized facilities and trained personnel to manage its radar-absorbing materials and other sensitive systems, which added logistical challenges and limited its operational readiness in austere environments. To address these limitations, the Air Force implemented the Single Configuration Fleet Modification Program. This initiative successfully reduced maintenance man-hours per flying hour by over 50%. The program consolidated various RAM configurations into one optimized design, improving maintainability and deployability while reducing the logistics footprint during forward operations. The maintenance burden particularly affected deployment capabilities. Units required specialized equipment and supplies when operating from forward locations. The complex maintenance requirements influenced the aircraft's availability rates, though these eventually became comparable to other tactical fighters of similar complexity. Temperature constraints also affected operations, as the RAM coating could not withstand excessive heat. This limitation, combined with the lack of afterburner capability, restricted the aircraft's performance envelope. The exhaust system required careful management through a non-circular tailpipe designed to minimize the infrared signature, further complicating maintenance procedures. These technical limitations ultimately influenced the F-117 service life. Despite its groundbreaking stealth capabilities, the aircraft's high operational costs and increasingly obsolete capabilities led to its retirement after 25 years of service. However, the lessons learned from addressing these limitations influenced the development of subsequent stealth aircraft, which achieved better balances between stealth requirements and conventional performance capabilities. The F-117 Nighthawk stands as a testament to human ingenuity and engineering excellence. This remarkable aircraft broke conventional design rules, proving that radar invisibility was achievable through its distinctive angular shape and specialized materials. Each aspect of the Nighthawk, from its faceted surface geometry to its sophisticated control systems, pushed aerospace engineering boundaries. Though technical limitations affected its combat flexibility and maintenance requirements, the F-117's success paved the way for modern stealth aircraft development. The lessons learned from its design, manufacturing, and operational challenges directly influenced subsequent generations of stealth technology. While newer aircraft now surpass its capabilities, the Nighthawk's legacy endures as the pioneering platform that ushered in the age of stealth warfare. Do you agree with this? If so, please like the video. Thanks for watching. Subscribe to the channel so we can discuss other insane engineering together.